Math 1325, we are working on section 5.4 today. This is putting everything together that we've learned in this chapter, plus stuff we know from previous, possibly math subjects, to sketch exact graphs of functions that we're going to see here. And it is a slightly different experience in MyMathLab than if you were doing this on paper somewhere. Some of these are multiple choice. It's just too hard to do the graph by computer for the exact details that would need to be shown, but we can do it ourselves while we are working the problem out. So I'm starting off with f of x equals negative 6x to the third minus 27x squared plus 324x minus 14. Negative 6x cubed minus 27x squared plus 324x and minus 14. So we can also use knowledge from other math subjects, as I mentioned. So something like with a polynomial here, if you know how n behavior works in algebra, an odd degree with a negative leading coefficient, that's going to have n behavior where it's rising on the left, falls on the right is one way to describe that, or it goes up on the left, rises on the left, and goes down or falls on the right. Because a positive odd does the opposite of this. The positive odd is falling on the left and rising on the right. So when you get a negative, it's just reversed. So one thing we know for sure already is that it's going to be rising on the left and falling on the right at the very ends. And just with that much knowledge alone, which has nothing to do with calculus, you might be able to eliminate some of the choices in the homework, but let's try to do this without looking at those at first. So we know that n behavior, and then also we could get a y-intercept very easily, negative 14. Y-intercepts are when you plug 0 in for x. So we definitely have to cross the y-axis at 0, negative 14. And there can only be one y-intercept of a polynomial. Otherwise, it wouldn't be a function if you had more than one. There could be up to 3 different x-intercepts, and you could use all the college algebra techniques that are taught in finding all the zeros, although that can take 15 or 20 minutes per problem sometimes. So we can hold off on that for now, and then let's do the derivative of this. Negative 18 squared minus 54x plus 324. So I did the first derivative. This is a polynomial. It would never be undefined. It could have 2 zeros itself. And hopefully if I divide everything by negative 18, then I'll get something that factors nicely. So you can even divide 0 by negative 18, it'll stay 0. So hopefully it becomes 1x squared. 54 divided by 18 is 3, so plus 3x. And 324 divided by 18 is exactly 18. So that would be negative 18. So we have x times x in the front for sure. That's the only way to get x squared. 18 could be 1 and 18, 2 and 9, or 3 and 6. With a negative in the back, you definitely get one positive and one negative in your answer. Multiply to 18, and then when there's a negative in the back, you're trying to subtract to the middle number. And then order matters since there's one of each, so it would need to be positive 6 and negative 3. Positive 6 times negative 3 is how you get negative 18. Positive 6 minus 3 in a subtraction fashion, that's how you get positive 3. So there are 2 zeros of the derivative, negative 6 and positive 3. These are our two critical numbers. So we have a chance to have local max or min at these two places. And we can make a number line and put them on there. I would pick 0 as a test point in the middle, 4 on the right, and -7 on the left. Plug these into the first derivative, and it's best to use the original version to make sure that sometimes dividing by a negative messes it up. So let's just plug it into the original. If we have a calculator that can handle that, it's no harder doing it in the harder version. So if I plug in, maybe if I turn the light up, that will help see this better. Okay, so I'm just going to plug in -7 where these two x's are right here and right here. So -18, parenthesis -7 squared, minus 54, parenthesis -7, plus 324. I got -180 for that. So the derivative is negative until you get to -6. From -infinity until -6, that whole section has a negative derivative. That means you're decreasing, which makes sense because we said the end behavior is starting up high, so it's obviously decreasing at first. It'll decrease all the way till you get to -6. And in fact, you can plug -6 into the original function to get the y value of it. But let's get all these first. The 0 is an easy one. The 0 is going to equal 324. F prime of 0 is 324 because the other two parts will disappear. That's definitely positive. And if you decrease first and then increase after you hit a critical number, that has to be a local minimum by the first derivative test. And then if I plug in 4 as my other test point, so I'm just going to change all the -7s to 4s. That's also -180 by coincidence. But most importantly, it's negative. So you're going to decrease first, then you're going to switch to increasing, and that's a local minimum when that happens. Then when you're increasing and you switch to decreasing by the first derivative test, that's a relative maximum. So both -6 and +3, they are local extrema. And then what we can do is we can plug them into the original function to get what the y value of them is. So -6 parenthesis -6 parenthesis cubed minus 27 parenthesis -6 squared plus 324 parenthesis -6 parenthesis minus 14. This will get me what y equals when x is -6. It's -1634. So this thing will go down quite a bit, and it's a little hard to draw it on this sketch, but down here somewhere is the coordinate -6, -1634. See, in college algebra, the students don't know how far down this goes. When they do their sketches, they find their x-intercepts. Apparently, it's something less than -6, and then they just kind of go down for a while before they come back up. But we can get exactly how far down that's going. This will decrease all the way till -6, and then at -6, that's a local minimum. So then you need to start increasing after that, and then you'll pass through this y-intercept, and then apparently when you get to 3 whatever is going to be the local maximum. So let's plug 3 into the original equation. 3. I got 553 when I plug 3 in. So that's like way up here somewhere. 3, 553. That's going to be the local maximum. So it's going to come down as low as -1634. It'll go back up through the y-intercept, and then when it hits here, then it'll go down all the way and connect up to the end behavior. And they'll end up being 1, 2, 3 x-intercepts, just like in college algebra, they could find those. And if we really cared about a detailed graph, we could find them too, but otherwise we'll be here for 3 hours doing each problem, because that can take another 15 or 20 minutes to find all those. So we have enough other points that we can get a good sketch without maybe finding those for right now, since that's algebra anyway. We want to look at the mostly at the calculus side of this. So one last thing we can do is we can do the second derivative. What if we take the derivative of this derivative? It'll be negative 36x negative 36x, and where am I? Here I am. Okay, and then minus 54, and the rest is 0, so minus 54. This is linear. It could never be undefined, but it can equal 0 once. So I have a chance to have one inflection point. And if I solve this for 0, it will also tell me when the graph is concave up and down. So at an x value of, these will divide by 18, so negative 3 over 2. Negative 3 over 2 could be an inflection point, so we need to check on another number line using the second derivative. If I plugged in, say, negative 2 and 0 would be 2 good checkpoints, and plugging 0 in is easy. The answer is going to be negative 54. The second derivative is negative anytime you're past negative 3 halves, and that's when you're concave down. And then negative 2 times negative 36 is positive 72. 72 minus 54 is 18, or more importantly, positive 18. So the graph is concave up. So you're concave up like so until you get to negative 3 halves, then you're concave down after that. And that means that spot at negative 3 halves is an inflection point. There's an inflection point at negative 3 halves, comma, whatever plugging negative 3 halves into the original problem gives you. So I'm going to do that one real quick here. So let's insert a negative. Insert divided by 2, parenthesis. Whoops. Okay, so let's insert, divided by 2. Insert a negative. Insert a negative, and insert a divided by 2. So it's negative 540.5, or if I needed it as a fraction, math, enter, negative 1081 over 2. So if they ever asked for the coordinate of it, they would probably want it written as fractional, negative 1081 over 2. For graphing purposes, we just need to know that's about negative 500. Negative 540.5. So remember, we got down as low as negative 1600 right there. So this was at negative 6. Negative 3 halves would be about right there. So this thing's concave up all the way till there. And remember, after this spot, it's increasing. It switched from decreasing to increasing. But all the way till negative 3 halves, it's still concave up. Then it's concave down the rest of the time, and my graph isn't perfect here, but it's hard to do this when the numbers are so large. But so let's just draw a sketch of it, and then we can always put the points in later. So it's going decreasing all the way to that relative minimum. And then when it increases at the negative 3 halves, that's when the bend changes. And it hits a high point and then keeps going down forever. So this way I've got the correct end behavior. I've got the y-intercept right there of 0, negative 14. The relative maximum was 3, 553. The relative minimum was -6 and -1600 and, or was it 1634? And then right about here, that's when the bend changed from up to down. That's -3/2 and -1081/2. So in a normal class that met in person for a class like this, where you're doing tests on paper, this is what you would probably do for a test, is show these points. You're showing the calculus points, really. The algebra can help too, but this is what you'd get graded on, is all the calculus points. This is a y-intercept, but did you get the local maximum? Did you get the local minimum? Did you get any inflection points? And then is everything else about the graph right? And any kind of college algebra knowledge can help too. For this, it's very easy to eliminate graph C and D instantly just from end behavior knowledge of college algebra. And then it looks like this is going down close to -1800, and I had -1600. This doesn't appear to go down quite as far as it should. Plus my local maximum was 553. That's pretty close to 700. Here it doesn't come anywhere close to 700. So this graph is pretty easy to tell that this is graph A, once you even have a little bit of the knowledge there. Okay, so now, I guess we'll do the graph towards the end. So now we have a quartic fourth power function for number 2, x to the 4th. See, now they're forcing you to do all this calculus stuff with the increase and a decrease in the concave up and concave down and inflection points. The other problem, all you had to know is a little bit of algebra knowledge, and you could have probably told what graph that was. -24x squared plus 135. So there's definitely a y-intercept of positive 135. It's an even power and a positive leading coefficient. So already we can, maybe I'll make a bigger graph this time. It's rising on the left and rising on the right. That's what happens with positive even powers. It has to have a y-intercept of 0, 135. There's 2 pieces of information that came from college algebra knowledge. And then, of course, you could also do other things in college algebra, like find all the zeros and other aspects like that. We know there can be 4 unique zeros. There's 3 turning points. There's some other college algebra knowledge you could use, but at this point, we're going to concentrate on the calculus side of this. So take the derivative, 4x to the 3rd minus 48x. There could be 3 critical numbers here because this is never undefined. It's a polynomial. I can factor out a 4x, leaving x squared minus 12. So x equals 0 is one critical number. And then on this one, you can add 12 and take the square root. The square root of plus and minus the square root of 12. Square root of 12 is 4 times 3 and 2 times 2. It's got a pair of 2's in it. So it's actually plus or minus 2 square root of 3. I won't be able to plug in 0 as a test point because it's one of the critical numbers. And we need to know square root of 12, approximately what that is. It's about 3.5. You wouldn't put this in an answer, but you just need to know where you're at so you know what test points to pick. 3.5. So I could pick 4 and -4 for those two. And then you could pick 3's, but I'm going to pick 1 and -1 for getting closer to 0. Plug all 4 of those into the first derivative. And all we care about is, are they positive or negative? Plug them in right here. So I'm going to do 4 parenthesis, -4 parenthesis, raised to the 3rd power, minus 48 parenthesis, -4 parenthesis. When I plug -4 into the first derivative, I get -64. So it's negative first from -infinity until I get to -2 square root of 3. The first derivative is negative, so that means the graph is decreasing first, which makes sense from my end behavior. Yeah, I should be decreasing first. Okay, then I'm going to switch from -4 to -1. And this is where graphing calculators help a lot. You can get these calculations really quickly instead of spending 15, 20 minutes calculating things. So 44, now it's switched to positive. So the graph is going to switch from decreasing to increasing exactly at -2 square root of 3. And that means you have a local or relative minimum there. There's a relative minimum at -2 square root of 3. That's the location of it. So about -3.5 is when you turn around. Then I can do 1. And I'm guessing it's going to switch to the opposite. That's what usually happens in polynomials. So yep, it switched to the opposite, -44. So now you're decreasing again. And you switched from increasing to decreasing. That's a local maximum. And then if I plug in 4, it's back to +64. So now you're back to increasing. You have another local minimum. And then all the way till infinity is when that's going to happen. So you're decreasing between -infinity and -2 square root of 3. You're increasing between -2 square root of 3 and 0. You're decreasing between 0 and 2 square root of 3. And then you're increasing between 2 square root of 3 and infinity. There's 2 sections of increasing, 2 sections of decreasing. So the function is increasing from, it was actually decreasing first, so let me put that one in first. -infinity until -2 square root of 3. Don't put 3.5 there. Did I go all the way there? No, okay. So there. And then it picked up and started increasing after that. -2 square root of 3. Oops. 2 square root of 3, all the way till 0, it was increasing. Then from 0 until 2 square root of 3, it was decreasing again. And then from 2 square root of 3 until infinity, then you're back to decreasing again. Or sorry, increasing again. So 2 sections of increasing, 2 sections of decreasing. That all came from the first derivative. Okay, there are relative extrema, 2 minimums and 1 maximum. They do want ordered pairs, so unfortunately we have to plug the 3 critical numbers into the original problem. Although 0 is 135, and that's actually the 1 maximum. There's 1 relative maximum at 0, 135. And there's 2 relative minimums. One's at -2 square root of 3, and the other one's at +2 square root of 3. And then we need to get the y values, although because the exponents are even, if you find one of them, the other one's going to have the same answer, since the even exponents will change negatives to positive. And you could even put in, you don't even have to put 2 square root of 3 in when you're just calculating. You can put square root of 12. So I can do square root of 12 raised to the 4th power minus 24 times square root of 12 squared plus 135. And it came out weirdly exactly to -9. So that means -9 is as low as the graph ever goes. And then based on the even exponents, I can tell that the other one's going to be +2 square root of 3, also comma -9. Whoops, got too many negatives, -9. Okay, then we're going to do concavity, but let's put on what we have here. So about -3.5, which is -2 square root of 3, that's when you hit -9. And then at +3.5, that's when you hit -9 again. So this will decrease till here, then increase till there, and then decrease till here, and then finish off up there. And when it's decreasing, I'll draw this a little better here. This is going to curve like a parabola, like a U shape, right through that minimum. But somewhere between here and there, it's going to switch from concave up to concave down. That's going to be an inflection point. So we can only tell that from the second derivative. So we need to do the second derivative and get when does it equal 0. That would be 12x squared minus 48. 12x squared minus 48 is the second derivative. And it's never undefined. And it equals 0 twice. I can add 48. Divide by 12. And that will be 4. So take the square root, plus or minus 2. Plus or minus 2 are two what are like critical numbers, even though they don't call them that. But if I plug in test points around 2 and -2 into the second derivative, I can tell if the original graph is concave up or down. So I would definitely choose 0 in the middle and probably 3 and -3. 0's nice because you're just going to get the -48. So it is concave down anytime you're between -2 and 2. And if I plug in either 3 or -3, the square is going to make them 9, so they're going to both have the same answer. I just have to do it once. 12 times 3 squared minus 48 is positive 60. So both of these sections are positive. And that means you're concave up on each end. So from -infinity until -2, you're concave up. Between -2 and 2, you're concave down. And then from 2 to infinity, you're concave up again. So it's -2 and +2. And if we want to know the inflection points, which we probably do, then we're going to have to plug 2 and -2 into the original problem. Although if I plug one in, the other one will have the same answer because of the exponents. So if I do 2 to the 4th power minus 24 times 2 squared plus 135, I'm getting 55 for that. So the two inflection points, these are inflection points because we switched from up to down and then we switched from down to up. -2, 55 and +2, 55 are two inflection points. So the graph is concave up from -infinity until -2. And then it does it again from 2 to infinity. And it's concave down between -2 and +2. And there's inflection points at -2, 55 plus 2, 55. Now do the graph. So that's what would help here is if this is -3.5 right here, when you hit -2, it would be somewhere like about here and there. Here is 2, 55 because that's 0, 135, and this is -2, 55. Those are the two spots where you stop curving like a parabola, like an upward parabola. It's all curved upward from here to there. I'm exaggerating a little bit. And then it'll curve upward from here to there, like a parabola. Those two sections are concave up. But then between these 3 points, that's when it's like an upside down parabola curved downward. So we've switched from concave up to concave down to back to concave up. These are all concepts that college algebra students can't do. They would never know where this local minimum is. They would just kind of sketch it roughly. They wouldn't know about this inflection point. They wouldn't know the y-intercept, but they wouldn't know about this inflection point or this local minimum. They would know the y-intercept, but they might not know that it's the local maximum actually. So it's definitely not A that's upside down. It's okay. It's definitely not D because that one doesn't even drop below the x-axis. We went down as low as -9. This one doesn't go below the x-axis either. So it's definitely this one right here. Come down to -3.5 and -9, and then go up to 0, 135, and then back down to 3.5 and -9. And it's hard to tell on this graph, but the inflection points are at -2 and +2. Okay, so see, this is what the majority of the section is about. Section 5.4 is they give you a function, and then you're just supposed to use any of this stuff from the past or currently. You can do domain and ranges from algebra. You could do symmetry from algebra. You can do intercepts from algebra. Critical points will help you do the increasing and decreasing. The second derivative helps on inflection points. Is it concave up or down? So just basically, here it is, go to town with it. And if you can figure out the answer in the homework or the test without doing the whole process, that's fine, but just make sure that you understand the full process. So maybe you have enough college algebra knowledge to know how to graph this, because we actually graph these in college algebra. X plus 6 over -x plus 8. Yeah. So this fraction is fully reduced, no way to reduce it. There's one thing that makes the denominator 0. That'll turn out to be a vertical asymptote. Set this equal to 0 and solve for x. X will equal 8. X equals 8 is a vertical asymptote. Horizontal asymptote, you have to look at the degree of the numerator and denominator. Both of these have a degree of 1. When they have equal degrees, then the horizontal asymptote is y equals the two leading coefficients divided by each other. So that would be y equals -1. If you plug 0 in for x, you can easily get y. And y-intercepts are always easy to find. It's the x-intercepts that sometimes take a long time. So I would just plug 0 in for x. There can only be one y-intercept anyway, at the most. But if you plug 0 in, you're literally going to get 6 over 8. So 0 3/4 is a y-intercept. Okay, then we could do the derivative. The derivative will tell us about increasing and decreasings. And this is a quotient rule, so I have to do second times the derivative of the first, which is just 1 since it's linear, minus the first times the derivative of the second, which is -1, over the second squared. Now, 8 is an asymptote because it makes the denominator 0. So 8's going to also make this denominator 0. That normally could be a critical number, but not if it makes the original also undefined. So the one spot that makes this derivative undefined is also making the original undefined, so that's not a critical number. And then we can try to see if the numerator ever equals 0, that will be possible critical numbers then. If I distribute a 1 here, it would just be -x plus 8. This double negative could turn into a plus, and then distribute a 1 here, and you'd get x plus 6. The negative x cancels the positive x. So the derivative answer is actually 14 over, if you were just doing what's the quotient rule derivative answer, it would be 14 over -x plus 8 squared. Well, this never equals 0 because the top never equals 0. The top's always 14. And the bottom is always going to be positive or 0, but we already know about the 0 point. The bottom can't be negative either because it's squared. So that means the first derivative is always positive. It never has any critical numbers. So there can't be any local maxes or mins. And it's always positive, so that means the graph is always increasing. The original graph is always increasing because the derivative is always positive. So with that much knowledge alone, you could eliminate any graph that shows a decreasing portion. In fact, C is always decreasing, and so is D. A and B are always increasing. And I already know the answer is A because the vertical asymptote was 8, not 0. In fact, there's a y-intercept of 0,34. So the graph, this is definitely A. And if you can get the answer right there, that's fine. You could also take the derivative of this and do it again and try to get the second derivative and see when it's concave up and concave down. But apparently it's concave up all the way till you get to -8, and then it's concave down after that. So that's another thing you could do if you wanted more detail to this. Okay, number 4. The original function is 5x over x squared plus 36. Okay, so we could get the... Now this doesn't have end behavior to worry about because it's not a polynomial. We could get the asymptotes, if any. The denominator would never equal 0 because anything squared is 0 or positive, and then if you add 36, the minimum of the denominator is 36. It's 36 and up. The denominator is always positive. It's never equal to 0, so we don't have any vertical asymptotes. And then in the horizontal asymptote, if the denominator has a bigger degree, then there's a horizontal asymptote automatically of y equals 0. So there is no vertical asymptote, but there is a y equals 0 horizontal asymptote. And then if you plug zeros in for x's, you're going to get 0 over 36, which is 0. So the one and only y-intercept actually is also an x-intercept. It's the origin 0, 0. So there's all the algebra knowledge we could bring into play without going further into other things like what are all the x-intercepts, which takes a long time. So vertical asymptote none, horizontal is y equals 0, and it definitely has to go through 0, 0. If I do the first derivative, second times the derivative of the first, which is just 5, minus the first, the derivative of the second would be 2x over the second squared. And again, the nice thing here is the denominator can never be 0, and it's going to always be squared, so it's all positive, really. The denominator is always positive. So if the numerator is either all positive or all negative, then we're going to know that we're always increasing or always decreasing. So I can distribute this and get 5x squared plus whatever 36 times 5 is, 180. And then this is just minus 10x squared. So the numerator is negative 5x squared plus 180. And then if I solve that equal to 0, I could subtract 180, divide by negative 5, which will bring you back to 36. So plus or minus square root of 36 plus or minus 6. Plus or minus 6, these are the two critical numbers. These make this makes the derivative equals 0 because it never is undefined. The bottom can never be 0. So we don't have any undefined places, but we do have 2 times where the derivative is 0. So these could be local maxes and mins. And I need to plug them into the original derivative, which might be a little tough, but here it is right here. And in fact, the x parts are all squared. So if I just plug 6 in, whatever answer I get for, well, I wouldn't plug 6 in, but if I plug in 7 and -7, let's say, and 0, if I plug in 7, whatever answer you get, -7 is going to give you the same answer. So in the numerator, you would have -5 times 7 squared plus 180. The numerator is -65. The denominator would be 7 squared plus 36, and then you square that. So it's -65 divided by 7225. That's negative for sure. So the first derivative is negative for anything less than -6 or greater than 6. So that means from -infinity to -6, you're decreasing. From 6 to infinity, you're decreasing. If I plug 0 in, this part will disappear. The top will just be 180. And if I plug 0 in here, the bottom's going to be 36 squared, which is positive. It's definitely positive when you plug 0 in. So then the graph's increasing between -6 and 6. So that means if you're decreasing first and increasing second after a critical number, that's a local minimum. And then if you're increasing followed by decreasing, that's a local maximum. So we have both a local minimum at -6 and a local maximum at 6. We could plug them into the original problem and get what the y coordinates are. In fact, plugging 6 in is easy. The top would be 30 and the bottom would be 72. 30 divided by 72 is it's a little less than a half. So 6 comma 1/2 roughly is where the local maximum is occurring. And then -6, the bottom's still going to be 72, but the top would be -30. So -6 and -1/2 roughly would be where the local minimum is. Okay, so let's take all that knowledge and see if we can figure out, okay, first they want this. When is it increasing? I already answered this. It's only increasing from -6 to 6 between the two critical numbers. It's decreasing from -infinity until -6 and from 6 to infinity. There is a relative maximum at 6, and then I guess we're going to have to put it in as, what did I say it was, 36. Plug 6 into the original problem. The top would be 30, and the bottom would be 72. 30 divided by 72, math, enter, enter, it reduces to 5/12. So they're always going to want simplified fractions. And then that means the minimum is -6 and -5/12. Okay, concave up, concave down. So now we're going to have to do the second derivative. Okay, so let me write the first derivative in a clean spot. The first derivative was -5x squared plus 180 over the x squared plus 36 squared. So the second derivative is another quotient rule. Second times the derivative of the first. The derivative of first would just be -10x minus the first, and then the derivative of the second is going to be a little messy, but this is the chain rule now. So you do your 2 times 1, which is 2, rewrite the base, decrease the exponent by 1, which would make it a 1, but then you'd also have to multiply by the derivative of the inside, which is 2x. All over the second squared, which would actually make it go from second power to fourth power. But the derivative, again, is all positive. No way it can equal 0, and therefore no undefined spots. So whatever makes the top 0, that could be our inflection points and or changing from concave up to concave down. Now you can't distribute that negative 10x into this parenthesis because it's squared. Here I would take this 2 and this 2x, make that 4x, and then you could put that out front, negative 4x, negative 5x squared plus 180. And then you would have this part remaining. Now, one thing that could help here is each of the three parts has an x squared plus 36. So I could cancel this, one of these two, and one of these four, and leave 3 left. That would at least help where I could distribute then. So negative 10x to the third minus 360x plus 20 x to the third minus whatever 4 times 180 is minus 720x over the denominator to the third power. Now see, this is a case where this is so messy and we're spending so much time just trying to find the second derivative that only because they're asking for the concavity are we even bothering to do all this. This would be a case if I was just graphing it, I would use other techniques to get the graph and not worry about all this, but this is good practice to be able to do this. So 20x to the third minus 10x to the third, that is 10x to the third. Negative 360x and negative 720x is negative 1080x. Okay, so again, the x squared is going to be 0 or higher. And if you add 36, that's going to be 36 or higher. So this denominator is definitely positive, even with a third power. The denominator is always positive. It can't be negative, and it can't be 0 even. The top could be 0, though. So that's all we're going to care about is what makes the top equal 0. It could actually happen 3 times. 10x to the third minus 1080x equals 0. So I can factor out a 10x, and that would leave x squared minus 108. So x equals 0, and then this is going to be plus or minus square root of 108. And if we need to reduce that down, it's 2 and 54. 2 and 27, there is a pair of 2's. And then there's even going to be a pair of 3's. So this would simplify if we need to write it as an answer to 6 square root of 3. But the square root of 108 is a little more than 10. It's 10.4 roughly, or just say 10.5. So we got 3 what are like critical numbers, and you can just use like 10.4 for, don't put that as an answer, but just on your number line so you know roughly where you're at. You would need to pick something like 11, 1, negative 1, and negative 11 and plug it into the second derivative to see when it's positive or negative. And is it going to switch from one to the other? Then we're going to get inflection points. So now I need to plug it into this right here, this big mess. At least the 1's and negative 1's would be easy because 1 cubed is 1, and this x times 1 would be itself. So if I plug 1 in, I'm going to get 10 minus 1080, which is negative 1070. And the bottom's going to be 37 to the third power. So 10 minus 1080 is negative 1070, and then 37 to the third power, negative 1070 divided by that, math, enter, enter, it doesn't even come out nice, Okay, let's see what they want for answers here. Use integers or fractions, okay. Okay, so, well, first of all, it was negative. So you're negative here in your second derivative. So that's a portion that's concave down. And then if I do negative 1, the bottom's going to be 35 cubed. That's positive, though. Negative 1 cubed is negative 1 times 10 is negative 10. Negative 1 times negative 1080 is positive 1080. So now you're going to get positive 1070 over a positive whatever. So that's definitely positive. So you're concave down between 0 and this about 10.4. You're concave up between negative 10.4 and 0. If I plug 11 in, 10 times 11 cubed minus 1080 times 11. Really all we care about is the top because we know the bottom's always positive. So if I plug 11 in, the top is positive, the bottom's going to be positive, so that's definitely a positive section. So then you're back to concave up again. And because you switched from positive to negative, negative to positive, those are both inflection points. And probably this one's going to turn out to be negative, and you'll get another inflection point there too. So if I plug in negative 11, and insert a negative, 10 times negative 11 to the third, minus 1080, oh, I did type that wrong, okay, times negative 11. Yeah, see, it is negative. So then you're concave down again. So you're concave down from negative infinity until you get to this negative 10.4, which is really negative 6 square root of 3 is how we should write it. Negative infinity to negative 6 square root of 3. They only want the up first, so forget that. It's concave up from negative 6 square root of 3 till 0. And then again from positive 6 square root of 3 all the way to infinity. And then it's concave down the other two times from negative infinity till negative 6 square root of 3. And from 0 to positive 6 square root of 3. There's inflection points, and unfortunately they want the coordinates, I'm guessing. Type in order to pair, yeah. So there's one of them is at, well, one easy one is at 0, 0. Like we said already, that's a spot. If you plug 0 into this, you get easily 0, 0, 1. Inflection point is 0, 0. I guess you don't need to put these in an order. So if I plug 0 into the original function, you get 0. If I plug in either 6 square root of 3 or negative 6 square root of 3, we're going to get different answers for those. But think of x squared. Think of 6 square root of 3 as square root of 108, actually. Remember how it was square root of 108? So if I do 5 times square root of 108, and that is 6 square root of 3, but I want to plug square root of 108 in for x down here when it gets squared, because that's easy to do then, rather than doing 6 square root of 3. Because the square of the square root cancels out. So the denominator is 144. The numerator is 30 square root of 3. And 30 divided by 144, math, enter, that reduces to 5 over 24. So 5 square root of 3 over 24, that's the y value when x is positive 6 square root of 3. So another inflection point is 6 square root of 3 with 5, let me make a fraction here, 5 square root of 3 over 24. Whoops. And then there's definitely one last one at negative 6 square root of 3, but the y value is going to be different, although it might just be the negative version of that. If I plugged in negative square root of 3 here, that would make the top negative 30 square root of 3. And if I did this, negative squared would be positive, so the bottom's still 144. So yeah, it should just be the same thing, negative. Negative 5 square root of 3 over 24. So those are really messy just because they're making me put the whole coordinate instead of just telling them the location of the inflection points. Okay, so put all this together. We said it's increasing. Where was it increasing? It's increasing. It's only increasing between negative 6 and 6. It's decreasing every other time. So you can eliminate some choices from that. It's definitely not A. That's decreasing between those. There were no vertical asymptotes, so it can't be those graphs. So it has to be B, where it's decreasing first, then it's increasing, then it decreases again. And then there's 3 inflection points. There's like a bend. It's concave down at first, but then it switches to up. Then it switches back to down. So there's 3 different inflection points there. And then minimums and maximums, negative 6 and negative 5 halves. That's this spot right there. And then positive 6 and 5/12 is right there. So the rest kind of checks out on that. Okay, so again, you can do this as slowly as you need, but we might be here hours doing all the stuff that these require, but we could use some college algebra knowledge maybe to speed this up. So x squared minus 25, that denominator can equal 0 twice at 5 and negative 5. So there's 2 vertical asymptotes, negative 5 and positive 5, and both graphs have that. These 2 are out. This is what happened in the last problem. And then I could get the y-intercept. Is the y-intercept something positive or is it something negative? Put 0 in for x, and you're going to get 6 over negative 25. So there's a 6 over 25 is like 0.24. So at negative 0.24, that's when you're crossing the y-axis. This one's crossing at a positive something, so that's definitely wrong. So just with some college algebra knowledge, I was able to figure out this was graph A. Okay, so ln of x over 18x for number 6. Well, if you remember the graph for ln x looks like this. And all log graphs go through the coordinate 1, 0. And then they also go through whatever their base is. The base of an ln is e, 1. And they have a vertical asymptote of x equals 0. And they have a domain of 0 to infinity. So I can't plug in 0. Normally 0 would make the denominator 0, and you would get a vertical asymptote there. And there really is a vertical asymptote even on a log graph. It's just that the log graph itself doesn't exist at 0. You can't plug in zeros and you can't plug in negatives, even though you can in the bottom, but you can in the top. So I can already eliminate graph D because it's existing in the negative side of the graph. That's definitely not going to happen. The rest of these are only doing positive sides, so that makes sense. So I've eliminated graph D so far. If I can't get a y-intercept because there's nothing there, I can't really do vertical and horizontal asymptotes. We already know there's a vertical asymptote anyway. So let's go to the derivative and see when it's increasing and decreasing. That could help. So this is another quotient rule. Second times the derivative of the first. Maybe remember derivative of ln x is 1 over x. Minus the first times the derivative of the second, which is just 18. This x would cancel this x. And then you got your denominator squared. So I'm getting 18 minus 18 ln x. And the bottom would have an 18x squared. I could actually write this twice, because there's a GCF of 18 in the numerator. And this 18 could cancel one of these two. So we're left with the simplified version of the derivative is 1 minus ln x over 18x squared. The denominator of that is only 0 at 0, but 0 is also undefined in the original problem. So we don't get any critical numbers from the denominator. When could the numerator equal 0? That would be the only question for critical numbers. And in other words, when is ln x equal to 1? It's equal to 1 right there. Ln x equals 1 anytime you plug e in. So e, 2.718, that's the one and only critical number here. So if I make a number line with e as the only value, and I'm going to plug it into the derivative, e is about 2.7, so I would plug in 3 and 0. Plug those into this derivative function right here. Oh, actually, you can't plug 0 in because it's undefined. So let's plug 1 in. Okay, so 1 squared in the denominator is 1 times 18 is 18. The bottom will be positive. What would be 1 minus ln of 1? So ln of 1 is 0, and 1 minus 0 is 1. So it's positive anytime you plug in something less than e. So the graph is definitely increasing first. You're going to increase from 0 to e. Not from negative infinity because there's nothing over there, but just from 0 to e it's increasing. If I plug 3 in, ln of 3 is not going to come out nice, but if I do 1 minus that, 1 minus ln of 3 is negative, and the bottom is definitely positive because it's squared. So that's going to make the derivative negative anytime you plug something in bigger than e. So then the graph's decreasing. It increases and then decreases. There's a relative maximum at e. By the first derivative test, e is a relative maximum. So we need to increase first and then decrease, and that's the only time it does that. So it's definitely not A. You definitely don't decrease first. You don't decrease first. It must be C. You increase until you get to E, which is 2 point whatever. Here's 15, 10, 5. So yeah, that could be 2.718. Increase till you get to 2.718, and then you decrease forever after. And I could go looking for the second derivative if you want to, but apparently based on the shape of this, it looks like it's definitely concave down at first. Maybe it switches to concave up after that, but I already have enough to know that the answer is C. Okay, fractional exponents on number 7. X to the 11 thirds minus x to the 8 thirds. So if you plug 0 in for x, these are both 0, so that means it definitely goes to the origin. Any graph not through the origin, that would be the y-intercept. But looks like they all do that. Maybe this one doesn't, but they definitely have to go through 0, 0. There's one quick thing I could do for algebra knowledge is the y-intercept is 0, 0. So the derivative would be 11 thirds x to the 11 thirds minus 3 thirds is 8 thirds. And then minus 8 thirds x to the 8 thirds minus 1 is 5 thirds. Okay, so if we set that, it's definitely never undefined. Cube roots are never undefined. set this to 0. I could add the negative part over to the other side of the equation. And then we could multiply by, which one's better to solve? I want to divide this way. So let's multiply by 3/11. These 3's cancel, so you have 8/11 here. And then if I divide by x to the 5/3, this is a rule of exponents in algebra. When you divide powers, you subtract their exponents. 8/3 minus 5/3 is 3/3, or just 1. So literally x equals 8/11 is the only time the derivative is 0. That's my one and only critical number. I could use 0 for something smaller than that and 1 for something bigger. Plug that into the first derivative. That's going to be easy, actually, plugging those two numbers in. Because 0 to any power is 0. So 11 times 0 minus 8 times 0 is 0. Oh, I did miss that one. Okay. 0 must be another. Yes, because you could factor out the 5/3. So I missed that, actually. 0 can't be a checkpoint. 0 is another critical number, actually. Because what I could have done at the start is I could have factored out an x to the 5/3. And then you would get x to the first and no x on this part. So this would lead to another time that it's equal to 0. Okay, so scratch that idea. 0 I can't plug in. I can plug in 1. That's nice. Definitely -1. And then I need something between these. I'm just going to use a half because there is no integer between those two. So plugging 1 in is nice because these will just both equal 1. And you'll literally get 11/3 minus 8/3, which is 3/3, or 1. But more importantly, it's positive. So our graph should be increasing anytime we're larger than 8/11. Plugging in -1, cube roots of -1 are -1. And then if you do it to an odd exponent, it will stay negative. If you do it to an even exponent, it'll turn to positive. So the front of this will be 11/3, and then the back will be minus a -8/3 or plus 8/3. So 11/3 plus 8/3 is 19/3, but more importantly, it's positive. So you're positive anytime you're less than 0. So the original graph is increasing until you get to 0, and it's increasing after 8/11. So is it also increasing in between, or could it maybe be decreasing, and then we'll have a max and a min? In fact, we'll get 1, 2, yeah, just one max and one min, possibly. Okay, so that's a little harder to do, but I could do this. 11 divided by 3, put that in parentheses, maybe 11 divided by 3, times, I'm going to plug in 0.5 for a half, raised to the 8/3 exponent, minus, parenthesis, 8 divided by 3, and then plug in 0.5 raised to the 5/3. And really all I care about is it positive or negative? It is negative. So yes, it increases first and then it decreases. So that's going to be a relative maximum first. And then after it decreases for a while, then it's going to increase and have a relative minimum. Okay, so this one seems a little wavy. We already eliminated graph D. Or no, I guess we didn't eliminate that one, but that one is out. Both D and B are out because these are decreasing first. We're definitely increasing first. So we increase until we get to 0, and that's why A's out, because this increases and then starts decreasing before we get to 0. So it must be graph C, which kind of looks like an x to the third graph. It increases till you get to 0, then it decreases till you get to 8 over 11, and then it increases forever after. And if I took the time to find the second derivative, I could figure out that it's probably concave down a little bit past 0, and then it'd be concave up after that. Okay, the final three problems are different. They don't give you the original function. So there's no way to like find the derivative and get all the increasing and decreasings and concaves ups and downs. But basically what happens is they tell you some information. This is kind of like solving a mystery. They give you some basic information about the graph, and it's really just guessing and checking until you eliminate all the other graphs. So part A is telling me, and these aren't really part A, but these are just like you're a detective and you've collected this evidence. So evidence A, it's continuous and differentiable everywhere except at -2 where it has a vertical asymptote. So any choice that doesn't have a vertical asymptote at -2 is out. Now it seems like this one's out already, see? It looks like that asymptote's only at -1 because this is going by ones. -1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah. So C is already out. It has the asymptote in the wrong place. It looks like the other ones all have it in the correct place. Okay, so C's out already from the first piece of information. The first derivative is greater than 0 everywhere it's defined. So in other words, everywhere except -2. If the first derivative is greater than 0 everywhere it's defined, then that means your graph is always increasing no matter what. So it can't be A because this one's always decreasing. And it can't be D because it's increasing for the first half, but then it's decreasing for the second half. B is always increasing from left to right. This graph's always going up. I already know the answer is B, and I haven't even checked everything. But just to confirm it, there's a horizontal asymptote at -1. Yes, that's true. The second derivative is greater than 0 in 2 different intervals. Those are concave up. So it's concave up from -infinity to -2. Yes, see how that's curved up all the way from there to there. It's also concave up between 1 and 3, which is there to there. See that curvature upward right there. And it's concave down on the other 2 intervals. From -2 to 1, it's concave down. And from 3 to infinity, it's concave down. So yes, this is all true for graph B. Now a few more pieces of information. Continuous and differentiable everywhere. So in other words, no asymptotes, and none of these have asymptotes. The first derivative is greater than 0 in 2 regions. That's when you should be increasing. So, and then when the derivative is less than 0, you should be decreasing. So you're increasing from -infinity till -3. No, this one's decreasing first. That's possible. That's possible. And this one's out. So you're increasing from -infinity till -3. Yes. Then you decrease from -3 till 0. Yes. Yes. You increase from 0 to 4. Yes. Yes. And you decrease from 4 to infinity. So yes, yes. So I couldn't eliminate B or C based on the first derivative. But maybe the second derivative will clear that up because the second derivative is less than 0 twice when it's concave down. It's greater than 0 once when it's concave up. So we're concave down from -infinity till -1. So that would be from here all the way around to about there. That's all concave down. Then from here to there is when it's concave up, which is -1 to 2. And then from 2 to infinity, it's concave down, although this one looks like it's doing the same thing. Okay, so the second derivative didn't help to distinguish between these two. The first derivative at -3 and at +4 is 0. Those would be relative maxes and mins. If the first derivative is 0, those are those high and low points. So when x is -3, Do you have a flat portion of the graph there? Yeah, see, that's a local maximum at -3, and it also happens at 4. Yes. -3, no, see, this one seems to be at -4 where that's happening, and this one's at 3. So C is wrong because they have it backwards. They're doing it at +3 and -4, but it's supposed to be -3 and +4. And then the second derivative is 0 at -1, 3, and at 2, 4. Those would be inflection points. The second derivative being 0 is an inflection point. At -1, +3, right there. See, that is the inflection point because it's concave down up to that point, and then it's concave up after that. And then at 2, 4, 2, 4, right there, 2, 4. That's where it stops being concave up, and then it switches to concave down. Although I knew that the answer was B after I got through evidence F. Okay, one last one of these, number 10. Continuous everywhere, so no asymptotes, okay. Differentiable everywhere except 1. That means there needs to be like a corner point or a vertical tangent line there. It looks like corner point is the answer, but they all have that. They all have a corner point at x equals 1. So that's why you can't do the derivative there. F of 1 is supposed to equal 5. So when x is 1 is y 5. 1, 2, 3, 4, 5. Yes. 1, 2, 3, 4, 5. Yes. 1, 2, 3, 4, 5. Yep. 1, 2, 3, 4, 5. Yes, that didn't help me eliminate anything. The derivative equals 0 at both 2 and 4, so those could be local maxes and mins. When x is 2, yeah, there's a local maximum there. When x is 4, that's not, well, see that it doesn't have to be a local maximum. It just needs to be kind of flat for a second. So that would just not be a local maximum or a local minimum. That would be where you're decreasing up to the critical number and then decreasing after it. So that's okay. That didn't eliminate that graph yet. 2, same thing. 4, same thing, yes. 2 and 4. 2 and 4. They all have flat points there, so that didn't help me eliminate anything. Okay, here's the first time we're going to get to eliminate something. The first derivative is greater than 0, which means the graph is increasing from 1 to 2 and 2 to 4. From 1 to 2, you're increasing. And from 2 to 4, you're increasing. See, that's out. This is increasing and then decreasing. It's not both increasing. From 1 to 2, you're increasing. And from 2 to 4, you're increasing. See, that's true on B. And C is definitely wrong because it's decreasing first. And D is wrong, it's decreasing. So we now know after evidence point E that the graph's already B. And then I can just confirm these last 4 things. Is the derivative less than 0 in these 2 regions? Is it decreasing in these 2 regions? From -infinity to 1, you're decreasing. Okay, that's possible. And from 4 to infinity, you're decreasing. Yeah, that's possible. The limit as x approaches 1 from the left is -infinity. The limit as x approaches 1 from the right is +infinity, but that's for the derivatives. So that's what it's talking about. This right here at 1, if you got really, really close to this corner point, you would have a very steep negative slope on the left side. So that's why it would have a -infinity derivative. And if you were close on the right, it would have a steep positive slope. So that would be a +infinity. So that is true. And then finally, concavity, the second derivative. The second derivative is greater than 0 or concave up between 2 and 3, and it's concave down all the rest of the time. Between 2 and 3, right there, you're concave up, yes. And everything else is supposed to be concave down. So that's concave down right there from 0 to 1. It's concave down from 1 to 2. And it's concave down all the way from here to there, which would keep going forever. So yes, H and I are also true. So even if you think you know the answer like halfway down, it's always good to go all the way through and double check. because maybe you made some kind of mistake early on and that's why you thought you had the graph you had. So if you thought you knew it after E, but you checked these other 4 and something was wrong in these other 4, then maybe you made a mistake earlier on. Now, if you're just doing homework, you can obviously just guess one, and if it's wrong, then they're going to give you another chance to do it. But on a test, that might be a good idea. Okay, so yeah, this section's a little long, curve sketching, but we're just putting together everything we know from algebra, along with what first and second derivatives tell us about increasings, decreasings, maxes and mins, concave up, concave down, and inflection points. All of that information helps us draw better graphs, and we can get to exact spots like how high and how low are these things occurring at, where algebra students don't know that. They just kind of draw quick sketches and they don't have as much detail to worry about as we do. So I got all 10 of these correct, and back here in the assignments, we're now 4 sections down and 3 to go. So we've done 5-1, 5-2, 5-3 last week. This week is 5-4, 6-1, and 6-4. And then next week we're going to do 6-5 in the review. So we're halfway done basically with the assignments, and I'll see you next time for Chapter 6.